going to do a video on predicting the number of hours of sunlight at any latitude on the Earth. So in astronomy, we learned that the tilt of the Earth is 23.5 degrees approximately from the vertical. This is 23.5 degrees. This is called the obliquity of the Earth. And on June 21st, on or about June 21st, the sun is directly pointing towards, the Earth is directly pointing towards the sun. So this is the sun here. So imagine this is June, let's just say for the sake of argument, it's exactly June 21st. So we want to know how many hours of sunlight people get on that day, depending on their latitude. So imagine we take this here and we're going to argue that this portion of the Earth is dark. Okay? And this portion of the Earth is bright. So we're going to do pretty simplistic. Imagine as if the Earth is a circle. Half of it is bright at any time. The other half is dark. And you could see here is if you live above a certain latitude, imagine that latitude. Here's going to be the equator. The equator is right in the middle of the Earth, so you should have equal amount of sunlight as dark. So you should have 12 hours of sunlight on June 21st and 12 hours of dark on any day. Actually, it should be the same for the equator because you're in the middle of the Earth. So above a certain latitude, you're going to have 24 hours of sunlight. And if you're below a certain latitude, you're going to have 24 hours of darkness on that day. Okay? So what's the general form of the equation here? So let's make this a little bigger here and see. So cut this in a vertical line. Cut this like this. This is dark, so this is going to be 23.5. This is dark. Okay, so this is the equator. So if I'm a person that's living at a certain latitude, let's say this is theta, this is the radius of the Earth, okay? So I am here. So what I want to know is what's the ratio of the length that I spend in sunlight to darkness, depending on my latitude. So if I'm living here, what's the ratio? What's this ratio of this to this? Okay? So in other words, it's a matter of getting the length. Okay? So if you look at this triangle, you're going to see this is your latitude right here. So you have this portion is the radius of the Earth. This is your latitude theta. Right? So what's this length here? From here to here? That's, this is r, this is theta, so it's going to be r cosine theta, right? This part here. So if this is r cosine theta, or it would be r sine of this angle, but because I'm doing it in terms of your latitude above the equator, theta is, this is the equator, theta is defined with respect to the equator. So it's going to be r times cosine of that angle, that's this little piece. What's this portion here? Okay? Focus on that piece now. Go down like this. Now what's this angle? That's 23.5, right? So imagine this is 23.5. I want to know this distance d. Okay? Well, look at this. If this is the radius of the Earth, what's this piece here? Okay? That would be r sine of theta, right? This side of the triangle, it's going to be r sine of theta. So this is going to be r sine of theta. So like this, like this. This is r sine of theta, this way, and this is d, and this is 23.5. And this is a 90-degree angle, so this is vertical right here. So what could we argue here? Tangent of 23.5 is equal to d over r sine theta. Right? So this extra portion d is equal to what? So d is equal to r tangent of 23.5 sine theta. So that's this piece. And then this piece we determined was r cos theta. So the amount of portion that any person is in the sunlight is equal to r cos theta plus d. Okay? So you have r cos theta plus d. That's equal to r tangent 23.5 sine theta. That's this whole piece that you are in the sunlight. Okay? Divided by the whole length is what? What's this whole distance? It's the ratio of how much you're in sunlight divided by the total distance. Okay? So the total distance, well, that's going to equal double r cos theta, right? 2 times the r cos theta. So this divided by 2 times r cos theta, this is going to be percentage of sunlight to the whole daytime. Okay? So number of hours of sunlight is equal to times 24 hours. Because the whole day is 24 hours. Let's apply this to LA. If you apply this to LA, notice what happens. The radius of the Earth cancels. So how many hours of sunlight will Los Angeles get on June 21st? So for LA, theta is equal to 34.5 degrees. So number of hours of sunlight is going to equal 58 hours. Okay? So that's 12 hours, and that's about 12 hours plus 3 hours plus about half of an hour, about 30 minutes. So let's say, let's see roughly if that makes sense. If sunrise occurs about 6:15 a.m., when will sunset occur? Okay? Sunset will occur 12 hours later. That gives you 6:15 p.m. Right? And then 3 hours later, that's going to give you 9:15, and then 30 minutes, that's going to give you 9:45 p.m. If sunrise was 6 a.m., then sunset will be 9:30 p.m. So about 15 hours and 30 minutes. Let's apply this to a latitude of what angle is it going to be that is going to give us 24 hours of sunlight. Well, if you argue over here, from logic, you could say it goes like this, it goes like this. If you want to be completely in the sunlight, and this is equal to 23.5, what should this angle be? 66.5. Right? So any latitude greater than 66.5, which is a complementary angle to 23, right? The 23.5 plus 66.5 gives you 90. Anything greater than 66.5 should give you 24 hours of sunlight. So if I put here greater than 66.5, greater or equal to 66.5, so I put into the equation 66.5, let's see what that gives me. So number of hours of sunlight. (24 hours above 66.5). How about if I put the angle 0? That means the equator. Angle 0. So I'm putting certain cases and seeing if it makes sense. If I put angle 0, what are you going to get? You're going to get cosine of 0 plus tangent 23.5 sine of 0 over 2 cosine 0 times 24. What does that predict? Well, cosine 0 is 1, sine 0 is 0. Cosine 0 is 1, so 1, 1 cancels. 1/2 of 24, 12 hours. So on the equator, the equation is predicting that you're going to get 12 hours of sunlight.